Hi folks, how are you? I hope you had a great morning. Please, if you can hear me, just thumbs up in the message. Okay, thank you so much. So today we will do the first of our review lectures. The topic we will review. So I'm showing you here the results from the form we did yesterday. So the topic most voted was procedure calls, so I will start with that one and then I will follow with the other topics as indicated by votes. So I will address one by one and yeah, until the time goes over. Okay, hope that is okay. As always, if you have any question, as this is a review lecture, I will try to go to slow down and I will try to address more answers and to stop to see if there are answers in the Q&A. Okay? Okay then. So the first topic you wanted me to review was procedure calls. So we have seen, I think that all of you know what is a function in a programming language, let's say C, Java, or whatever, right? So a function is you have in your code in any programming language is like a block that you call, and if it's inside a function, is because you plan to repeat that code multiple times, right? So a procedure is just like a function, is a routine that performs a specific task. So as I have mentioned, it's used to make the programs more structured, and it allows to be to reuse that part of the code. For instance, we have here a simple procedure. Let's say we have a box here. In this case, the procedure just swaps two values. So this function or procedure will have input values, something will happen inside this box, and it will generate output values. In this case, the procedure is just swapping the values. You could have a function for adding the values or for doing any other kind of operation, but we will have always the same pattern. Input arguments, something happening in the procedure, and output arguments or output data. Okay, so for instance, in a high-level programming language like C or Java, so this will have this shape. So we will have, let's say, two variables here, A and G, and then we will have a procedure or a function that in this case we have called swap, but you can name it as you want. And in this case, the arguments for that call are F and G. So at some point in my code, this function will be defined, and here you will do the things you want to do inside that function, and then you will return again to where the call was done, and your program will continue from here. Okay, so the flow of the program will be like here from up to down. At this point in the swap function, it will jump until the procedure, where the procedure is declared, it will execute those instructions, and in the return it will return again. I continue here with the rest of the code. Okay, in this case the rest of the code is this instruction. So the flow, as I have mentioned, is those three instructions are executed, then there is a jump to this procedure, those instructions are executed, and then it returns back to this instruction, and the code continues from here. So how this translates into LegVA? So in LegVA, you know, LegVA is assembly programming language, is not a high-level language, so we need to do extra steps in order to perform these calls that are managed implicitly in high-level programming languages like C. So in LegVA, what we need to do is, before calling a procedure or a function, we need to place the input data in registers which are for that purpose. In this case, are registers from 0 to 7 are registers for placing input parameters or input data for the procedure. Then I will call the procedure or the function. After that, what we do is we need to do that in LegVI because, as I have mentioned, it's a low-level programming language, it's assembly language. So in high-level programming language, I don't need to worry about the storage and anything. Everything is done implicitly, but here I need to manage it. I need to say, okay, if inside my function I'm going to use, I'm going to need storage, I need to acquire that storage. Then I will need to do the operations I want to do in the procedure, and I will also need to place the result in the excuse me. I will need also to place the result in the parameter register for the caller for having those results when the program returns to the point the procedure was called. And finally, I will return to the place in the code where this procedure was actually called. Okay, this return address or the place, the instruction which I need to execute once I'm done with the procedure is stored in a special register which is called, in this case, is register 30, which is called the link register. Okay, LR. So let's see which are the instructions we use in LegVI in order to call a procedure and in order to return from a procedure to continue the execution flow. So for instance, when we want to call to a procedure, we will call this instruction BL, which is branch with link, and here we have the procedure label. By procedure label, I mean the name of your procedure. It could be swap, it could be procedure 1, it could be whatever you want. So here this will be a label which will have been defined at some point, at some place in my code by the programmer, and this is the instruction I use. What does this instruction? Apart from going to the place in your program where this procedure label is declared, apart from that, it puts the following instruction, the instruction after BL, it's added into the link register, into the register 30 in this case. Why? Because once my procedure has finished, I need to come back and continue the execution flow, and I will use this this register. Okay, so and inside the other instruction that we use is once we are inside the procedure and we have finished, we need to return to the place where the procedure was called, and this is done with this instruction BR, which is branch to register, and in this case we use the register LR, the link register. Why? Because it's the register in which the instruction BL has stored the instruction following the procedure call. Okay, we know that what actually happens is that this in this instruction is that the link register, the address in the link register is copied to the program counter. And remember that we know what is the program counter. The program counter tells us which is the next instruction to be executed. We will see an example now. Let me check if you have any questions for that. So there are no questions related to this, to what I'm explaining. So for other questions regarding the assessment, I will answer them offline. Okay, so let's see an example then. So imagine now in LegVI. So we have this is our program. We have some previous code. I don't mind the previous code we have here. It can be whatever. And at this point, I'm calling the procedure. Okay, in this case, my procedure is called swap, but as I have mentioned, it can be called however you like. So you can put here any name. So what will happen here? So here, what will happen is that instead of continuing the execution of the add instruction, this BL will jump to a place where the swap procedure is declared. Apart from jumping to this place, it will also store the address where this instruction is. Why? Because once the swap procedure finishes, the execution flow will continue with this instruction. So then, when I have this, when we have this instruction, it will jump from here to here, but it will store the address of this instruction in a special register, register 30, or the link register, in order to be able to return here once the procedure has finished. So then from here, I jump to the procedure, I do what I want to do in the procedure, in the swap, and once I'm done, I return the control to continue the execution flow. I do this by using this BR instruction and the LR register. So in the LR register, in the link register, remember that we have noted the address of this instruction. So what will happen here is that it will come back to this instruction. Okay. Okay, I see some question that people are saying that the most confusing part is the stack memory and this part. So yeah, so we will be in that part soon. But I think if we understand this initial part, I think it's okay. So I will go more quickly here, and then we will go. Someone is asking why it is safe in register 30, because 9 plus 10 plus 11 is 30? No. So whatever you are doing in this instruction, the returning address will be always safe in this register. This register cannot be used by the programmer. It's used for storing the next instruction after a procedure. And whatever instruction you have here, the register in which the next address will be saved is 30. So here is just a coincidence that the sum of the registers are 30. So it doesn't matter which instruction you have here. So it will be stored, the address of this instruction will be stored in the register 30. Okay, so we already know what is the program counter, and yeah, so I will show directly you an example. So imagine that the program we have seen, all the instructions are in these memory addresses, and this will be the value of the program counter, and the program counter tells me in which address is the instruction I need to execute. So, and as each instruction occupies 32 bits, so the program counter will go increment in 4 by 4, because remember that the address is byte address in LECbyte. Okay, every address points to 1 byte, 8 bits. So 4 by 8, 32 bits, which is one instruction. So I will have here the first instruction, which is in this address of memory. Then I will have the second instruction, which is in this address of memory. So what will happen here is that when I execute this instruction, instead of going to the following instruction, I will go to the swap instruction, which is in address 12. And apart from jumping from here to here, this instruction will also record that, okay, the next instruction once the procedure finish is in address 4. So I save in register 30 that address 4. And by doing this, once I'm finished and I want to return back where I was when I call the procedure, I just go and look, okay, in which address is the next instruction? In address 4. So I go to address 4 and I execute that instruction. Remember that we have mentioned that those instructions actually in hexadecimal are usually represented in hexadecimal for clearness. Okay, so it will be the same as we have some previously with decimal, but in hexadecimal. Okay, and when we call a procedure, we need to store we need to make sure that if we modify some registers, we need to preserve the value of those registers. What that means? For instance, if inside my procedure I modify the registers 19 from 19 to 27, I need to keep the result in those registers. I need to keep the result that they had before calling the procedure. On the contrary, if I'm using registers from 9 to 15, which are temporaries, I can modify them in the procedure, and I don't need to keep to restore the values they had before calling the procedure. Okay, and here you can see that the link register is a special register which is actually used for the returning the address, and the value in this register I need also to preserve it on a call. I need to save it. I cannot modify it, because if I modify it, I will not be able to return to the execution flow once I finish my procedure. Okay, so this is what I have already mentioned. Excuse me. And the registers here from 0 to 7 are the ones we use for the input arguments and also for the output arguments. Okay, and I obviously can modify them in a procedure because they are for that purpose. Okay, so this is another example in here. Well, I think that this is clear, so I will try to go to the stack thing. So here I'm just mentioning that what we usually do is that we store the arguments in registers from 0 to 7. Okay, but what happens if we need more than a register? Because here I have said that we have only 8 registers for inputting and outputting data to the procedure. So what happens if I need more than 8 registers? Is then when I need to use the stack, which I think is the one, which I think is the stack. I think is the topic which is more confusing here. Okay, before we jump to the stack, let me check if we have any question. Yes, I will upload these slides. These slides are actually from lecture 4, so there is nothing new here. So you have already them. Some people is asking very confusing questions. So how do you know which numbers to use? Register 10, register 21. So at this point you should know. So this is a decision of the programmer. Okay, you are the programmer and you have those registers available. It's like variables in C. You can use any variables you want. So here you are limited in the number of registers you can use, but you are the programmer and you decide if you want to store a given value in register 9 or in register 21. But well, that's a bit surprising. Okay, at this point you should know that. Let me check if there is any other question. Okay, someone is getting also, some people is getting confused. So here, I'm not saying that this instruction at 9, 10, 11 is doing what is in green. What I'm saying here, so I assume that at this point you know that this add is doing register 9 is equal to register 10 plus register 11. Okay, what I'm saying here is that when I call this instruction, apart from jumping to this procedure here, I going to store the address of this instruction in a register called LR, in a register 30. Why? Because when I finish the procedure, I will need to go back to that instruction, and I need to store at some place the address of this instruction. So this comment here in green is just saying that the returning address, the link register, has been saved in register 30 when I have called this function, and when I call the branch register LR, I just go back to the address saved in register 30. Okay, but I'm not saying here that the comment in green is what this instruction is doing. Okay, I think that is clear, but just in case. Someone is asking if procedure calls are the only topic I'm covering today. So as I have mentioned, I will cover topics one by one. So as soon as I finish one, I will finish the other. Okay, let's go to let's continue with the stack, which is the most. Okay, so we were saying, what if we need more registers than the ones we have in the 8 registers for input and output data of the procedure? So then we will need to use the memory, and for that we have something that we call a stack, and the stack is what we call a last in first out queue, and we have a pointer, a stack pointer, which points to the most recently allocated address in the stack. To push an element, when I say push in the stack, I add an element to this stack. So if I'm inside my procedure and I need extra space, I can push some elements to the stack, and when I'm done, I can pop elements from the stack, which is actually removing them. And what is interesting here is the stack grows from higher to lower addresses. So let me show this graphically. So imagine this is the stack memory. So the top address is FF in the hexadecimal, and let's say that the lower address is 00, just for clearness. So for instance, if I'm inside a procedure, I will have the stack pointer, which is pointing to this address. Why? Because the most recent element was introduced at this address. So this means that I have here, for instance, the content of one register, register 20. Remember that each address points, in this case, to 32 values, so to 32 bits. So one register contains 64 bits, so I need 2 addresses in order to store one register. So in this example here, I have one element, one register in the stack, and that register is taking 2 addresses, and my stack pointer initially points to here. So is this clear? Someone is asking, is it just addresses what get stored on the stack? No. In the stack, what you get, the addresses are just for accessing places in the stack. So initially, if your stack is empty, you only have addresses to access every. In this representation, for instance, you need the address is like the index for accessing every row in the memory, every register in the memory. So in the stack, what we have is, by default, we have all addresses, but we have like a table like this, an address and the content at this address. So this is what we have in the stack. Okay, we have addresses, and each address points to some content. Okay, so imagine now that I want to add an element I'm using my procedure and I need extra space, and I have this initial stack memory. So, and I want to add an extra element. So what I do is, okay, I update the stack pointer because I'm going to add a new element. As I have mentioned, the addresses grows from high to low, and in this case, so I update the pointer. Why I move 2 positions and not only one? Because as I have mentioned, registers in LEGVI occupy 64 bits, and each address in the stack memory each address points to 32 bits. So I need 2 addresses for storing a register. So in this case, what I have done, I have updated the value of the stack pointer. Now it points to this address here, and I have also stored the contents of one register. In this case, I have stored the contents of register 19. It can be any other register, the register you would like to keep. Okay, is that clear? Okay, so now imagine that we want to remove because we are going to finish the procedure and we want to remove the elements we have introduced in the stack because we don't need anymore them. So what we do is we just remove, okay, we remove this pointer and we say, okay, we are going to remove the register 19, which is the one I have introduced in my procedure and the one I don't plan to use anymore. So then I remove the pointer and I make that pointer point again to the initial address, and I remove also the content that was here in the stack. Okay. Some people is asking what I will ask in the test. As I mentioned, I'm preparing a practice test. So, but you will have you need to understand what I'm saying, because in the practice exam, what I'm going to ask you is I will give you a code and you will need to complete the stack, the contents of a stack after executing one code, something like that. Actually, what I'm doing now. So, for instance, imagine now that we have this code. So hopefully all of you understand this code. Here we are inside a procedure, okay? We have already called the procedure with the instruction, and we are here in a procedure which is called swap, and we have those instructions here. So what are we doing first? First, what we are doing is, as we plan to use register, as we plan to use register 20 and register 19, and as we have mentioned, those registers must be preserved on a procedure call, I need to store the value of those registers before using them. So why I want to store their values? Because in the procedure, after I have used those values, I need to restore them to the initial value, because the specification of LECV8 says that register 19 and register 20 must be preserved on a procedure call. So for storing them, what I do is, okay, I have my stack pointer. It's pointing to a position, to an address, and I know that I'm going to add 2 more registers. So I will need to add 2 elements. And remember that if you go back to the initial lectures and to the initial lab, in order to modify memory arrays or memory addresses for each element, we needed to multiply it by 8, because the memory was byte address. Okay, every address points to 8 bits. So here, if we want to actually modify the stack pointer for pointing for storing 2 elements, I need to increment it by 16. Okay, so what we are actually doing is, initially our pointer was here, so I increment 2 positions for one element and another 2 positions for another element. So in total will be 4 positions in the address. But as I have mentioned, each position, the memory is byte address, so each position points to 8 bits. So we need to multiply these 4 jumps that we are doing by 8. So this is what I'm actually doing here, okay? So with this instruction in red, what I'm doing is moving the stack pointer to this address. Why? Because I will need to add two registers, one here and another one here. And by moving the stack pointer to this position, I have incremented it by in this case, actually 16, but what you can see in the screen are like 4 addresses, okay? So this is what I have actually done. Let me check. There is someone asking if the value of the link register of the LR will stay the same until the store instruction is called. So the link register will stay the same until we return here to the place where the procedure was called. What could happen is that if inside a procedure you call to another procedure, then you will need to store the link register in the stack, call the new procedure, do what do you need to do there, and probably at this point the link register will change because it will be like having nested procedure calls. But if you only call one procedure and there are not nested procedures, the link register will be the same until you return. Okay, that's the purpose of the link register, storing that address until you are done in the procedure. Okay, so let's continue with the example. So we have modified the stack pointer because we are going to add 2 items. Okay. So, and the stack pointer now points to this address, and now we can use this space in my procedure. What I'm doing now in these instructions, with the previous instruction, I have just modified the pointer, but I have not stored any information. Okay, I have just moved the stack pointer from that position to this one. But now I need to actually store the data I want to store in the stack memory. For that, we use the store instructions that the data instructions we have in LECVI. In this case, with this instruction, we are storing the content of register 20. Where? So we have 2 positions. One is with the stack pointer pointing to 0, which will be this one, and the other one will be with the stack pointer +8, which will be this one. Okay. So therefore, in the first one, we are storing register 20 in the address pointed by SP8, which is in this one. Okay. And then we are doing the same with register 19 with the 0. Okay. I think there is a mistake here. Actually, they should be changed. So I think that what we are storing here should be register 19, and I'm going to try to modify this. Because the indexes mention that. So what we actually have is this, okay? So we have register 19 in SP0, which is this position, and register 20 in SP +8, which is this position. Okay. Okay then. So now imagine that we do whatever we want to do with our procedure, and we do what we want, whatever we want to do. Here I have done those instructions, but it's just for completeness, but I'm not interested in those instructions. Here I'm interested in whatever I have done with register 20 and register 19 inside my procedure. I need to restore it to the value those registers had before calling the procedure. So here I have stored the values of register 19 and register 20 before starting my procedure. And whatever I do here with those registers, before returning back, I need to restore those registers. Why? Because the specification of LECVI tells us that those registers must be preserved, so they cannot be modified. So what I'm actually doing in those three instructions. So remember, we have stored in those positions register 19 in register 20. So what we are doing is just loading them. So we know that at the position 0 in the stack, we have register 19. So we load, in this case, the content of the stack to register 19. And we do the same with the register 20. Okay, we restore the initial result. So the result we have saved here in those two instructions is restored here. So if I have changed those registers here, those changes will not be preserved. They will be removed by those instructions. And once I have used those registers, I just update again the stack pointer. And with this, I'm done. So what I have done is I have used the registers I have in here, and I again put make the stack pointer pointing to the initial address. Okay, and here I will just go to return to the caller, and as we have seen, this will just see what address we have in the ring register, and we'll jump to that address. Okay, so before we continue, let me check if we have any as well. So someone is asking if there will be in the test encryption. So the encryption was just for making it more funny, the lab, but you will have something similar to a spreadsheet. What I'm working is I'm trying to see if instead of a spreadsheet we can just have a table on Canvas, on a Canvas quiz, and just you need to fill that table in the exam in the Canvas, on Canvas. And this is what I'm preparing actually right now. I'm seeing if those things can be just inserted in a Canvas quiz, and if it can be done, you will have a practice test exactly with the method I will use in the exam. Someone is saying, asking if the stack is a kind of like temporary storage to make room until there is enough room again in the register. So yes, it's exactly that. It's what we have mentioned before. So we only have 8 temporary registers. So, and if we need more, we need to use, we can use the space in the stack for that, for anything I need in my program. Okay, that's exactly. Okay, so then to see it in, okay, let me check if there is another question. Someone is saying if it is not last in, first out. Yeah, so I think this is what I have mentioned. At some point we have said that the stack is, yeah, we have said that is a last in, first out. So the last element I insert is the first element I remove. Yeah, I don't know if maybe there is something. Yeah, so here we save register 20 and then register 19, and sorry, and then when we remove them, we are doing it in the other way. So we first remove register 19 and then register 20. Let me check, maybe there is something wrong. No. Okay, yes, so the slide was correct. I have, yeah, so the slide was correct in the beginning. So the problem here is that let me see if I can. The problem is that I had we have modified the stack pointer. Okay, so it was correct in the beginning. Yeah, so the confusion comes because here you see I have modified the value of the stack pointer. So the stack pointer now is pointing to this value. So if I subtract here 0, from the stack pointer, I'm storing actually register 19 here. If I subtract 8, the stack pointer is pointing here, and I'm storing here register 20. Okay, so it was correct in the beginning. Sorry, and then it's actually a last in phased out. Okay, many thanks for pointing it out. Someone is asking if we always need to assign the stack pointer manually. So yes, this is the problem of assembly programming, that you need to do all yourself. So in a high-level programming, you don't mind about that. Everything is done implicitly for us. But here, if you use space in the stack, you need to manually modify the stack pointer. Okay, so if we want to see this in one slide, so imagine that before calling the procedure, the stack pointer was pointing at some address. Once I call my procedure, I use this stack address and I add here elements. And when I finish my procedure, I delete those elements, restore the stack pointer to the initial value, and just return back to the caller. Okay, let me check if there is there are more questions. Okay, so I don't see any. Someone is saying in slide 25, stack pointer point to the most recent added W. So the stack pointer is pointing to the most recent added word. So the last register included was register 19. So the last register removed will be the first, the last register inserted will be the first register removed. So this is what we are actually doing in the code. So the last register stored is the first register removed. Okay. In this case, this register will be the first remove, the last in, the first out. Okay. So remember that here the stack pointer the addresses goes from high addresses to lower ones. And the stack pointer, if you see here, when we want to add an element, we subtract positions to the stack pointer. Okay, so this is something that could be a bit confusing, but it is how it works. So the addresses go from high to low, and the stack pointer, if we want to add an element, we subtract an address from the stack pointer. So maybe that is what can be a bit confusing. Okay, so now let's jump now to see. Okay, so apart from the stack pointer, if we need additional memory for storing, let's say, a local array or something like structure. So the stack is for registers I need to preserve, but if I need to declare new arrays or new data, what I can use is also something called the procedure frame, which is actually part of the stack, which contains, apart from the safe registers, also local variables and so on. And for knowing which space is being used by one procedure, apart from the stack pointer, we have the frame pointer. So the stack pointer points to the last element used, and the frame pointer points to the first element used. So with this, we have all the space used by a procedure. So imagine that initially the frame pointer is pointing here and the stack pointer is pointing here. And imagine that I start a procedure here. So the frame pointer for this procedure will point to the first position of the stack memory used by this procedure, and the stack pointer will point to the last one. And with this, I have complete control of all the addresses that I'm using from the stack memory in my procedure. Okay, and the frame pointer, similarly to the stack pointer, is a pointer that I should manage if I'm adding, apart from say registers, I'm adding local arrays or something like that. Okay. Okay, someone is asking if we can use any register as long as it is in the correct range. So yes, you can use any register, and you can use in any order. You can use first register 22 and then register 19. This is a decision of the programmer. Okay, what you need to consider is that there are some registers which are temporaries, which means that if I have a value in register 9, for instance, which is a temporary register, and I call a procedure, when the procedure return, maybe that result is not there, okay, because it's a temporary one. If I want a data to be preserved, it must be stored in a register preserved on a call, for instance, register 22, but I can use any register and I can use in any order I want. So you don't need to use register in incremental order, okay? And now I would like to show you how this memory is the stack is related with the memory where the program is. So we have already seen this. So starting at address 0, well, we have some reserved memory here, but our program will be stored here, in which is called text memory. Then we have static data for constant data which not changes, and here is the stack, and here is what we are using in the procedure and what we have mentioned today. And now you probably understand why it grows from up to down. So because here we have some space, but we don't know how much space will use the text segment or the static data. So we just start the stack pointer from the top and start using the stack from the top to down. And with this, we can use all this space from here for my stack, and I can use the space from lower addresses to higher ones for my program. So here in the text memory, as you have seen in the labs, in the text segment is my program. Here I will have static data, and then we'll start the dynamic data and the stack. Okay. And this is what I have actually mentioned, that we have higher memory addresses, lower memory addresses, and the stack grows from up to down. Okay. Someone is asking why the frame pointer moved down. As I have mentioned, the frame pointer as well as the stack pointer, we are using addresses from high to from high to low, because we are using the space from the space from the top to the down. Okay, because the lower addresses are used by the program and other things, and in order to have it in a different place, we just start from the top, and both the stack pointer and the frame pointer grows down, because as I have mentioned, if I use some space here, I will modify this pointer and this will point here. And similarly, for the frame pointer, if I'm using this space from my procedure and then I have another procedure here, this frame pointer will grow down in the direction from up to down. Okay. So I will finish answering some of your questions here in the chat. Hopefully this has been helpful. If you have any more questions, you know that we are available using the ticketing system and also by email. And tomorrow will we continue reviewing the topics you have voted. And yeah, have a nice rest of the day, and see you tomorrow. Okay, many thanks. Bye bye. See you.